Looking good. So I've got this, and it's out of the way, and I got my pen. Let's do this. Okay, so welcome to our first algebra video. We're going to be talking today about some stuff from chapter 6. Specifically, we're going to be doing 6.7, which 6.7 is all about using formulas. And we're going to do some applications of rational equations. Woohoo! All right. So we're going to start this off by just looking at formulas. So hopefully you remember formulas from all the way back in chapter 1 are all about equations that describe specific relationships between a bunch of variables. But we're going to be looking at how to use formulas to do some different things. So we're going to be applying this a little bit differently than what you might expect. So specifically, we're going to talk about solving for a specified variable. Now, as you may remember, solving really only has two main components. And that's the idea of the addition rule, which it's horribly named because it's also the subtraction rule. And then the multiplication and division rule. Okay, so these were fairly simple. The basic idea of the addition rule is if I have two things that are equal, I can add something to both sides and it still remains equal. So whatever I add to one side, I also have to add to the other. And then the multiplication division rule, and obviously you could do this with subtraction rather than adding c, you subtract c. If I have two things that are equal, I can multiply on both sides and it's still going to be equal. And the same thing with division. So whatever you do to one side, you have to do to the other, and that's all there is to it. Hold on. I lost track of where I'm at. My mouse has disappeared, which is helpful. I don't know if I like this. Okay, let's do some examples of some solving. So here we go. So one thing that's nice is that for these in particular, you're always going to be doing the same thing. We're going to be solving, oops, it's an L, for the specific variable. That's awesome. I have palm rejection on, but sometimes it still picks up stuff. Sorry about that. Solve for this specific variable. So we're going to have some specified variable that's being asked for us to solve. So for this first one, I'm going to do s equals 1/2 a plus b plus c, and we're going to solve this for c. So I'm going to be looking for trying to get c by itself. So I want to get to this guy right here. Yeah. So in particular, if you look at what's happening to C, it's being added to both A and B, and then it's got a 1/2. So whatever happens last, you have to get rid of first. So the first thing I'm going to do is I'm going to take that 1/2 and get rid of it. So remember, one of the things we do is that we are doing opposites to get rid of things to get back to C. So since I'm being multiplied by a half, that's the same as dividing by 2. So I'm going to take this and I'm actually going to multiply both sides by 2 because I know that will cancel with the 2 in the denominator there, and then I'll just get a 1. So I can update this now and say I have 2s, but that s just doesn't want to draw, doesn't like curves, is equal to, and I don't need the parentheses anymore, so I can say a, b, and c, because I needed the parentheses because of the times 1/2. That's gone now, so we're good. So what I want to do next is I want to get rid of a and b, since they're attached to c. So I'm just going to subtract a from both sides to get a to cancel, and subtract b to both sides to get b to cancel. So I've written this kind of weirdly. A, b, and s are in all different variables, so they are not like. So I cannot combine them. So I'm just going to write 2s minus a minus b, and that will be c. So there we go. There's my answer. So that's how you solve for a specific variable. I gotta get this to scroll again, which is the only place I have difficulty. All right, let's solve for another variable. Oops, I gotta go back to pen. No. Oh, God. Yep. This is just, sometimes it's the best thing, sometimes it's the worst thing. I think I might need to pause for a second. I'm having some difficulties. And we're back. Okay, so next up, we're going to take a look at another equation, and we're going to solve it for a different variable. So here I'm going to have a is equal to little a plus n minus 1 as a quantity times d, and we're going to solve this for d. So again, I'm going to look at what's happening to my variable of interest d. It's being multiplied by something and then has something added, so whatever happened last I'm going to get rid of first. So the first thing I'm going to do is actually subtract little a. And since little a and big A are different variables, there's nothing going to happen there. So these two are going to add to make nothing. And over here I'll get n minus 1 times d. And then since it's times d, what I'm going to do to get rid of n is I'm going to be dividing by it. Whenever I do to one side, I got to do to the other. So I'm going to divide by an n minus 1. And there we go. So there's the value of d. So I'm going to rewrite this so it looks a little bit nicer. So I would say is d equals to big A minus little a over n minus 1. Hopefully you like the way that one looks. Let's move on to C. So for C, I'm going to be doing PV equals nRT. And if you've had science already, you know that this is called the noble gas law. Look at this. You may know that it's the noble gas law if you've had science recently. And P is pressure, V is volume, T is time, N is a constant, and R is a constant. So there you go. Gas. Woohoo! We're going to solve this for T. Now, my T looks weird, so we're going to just go ahead and fix that. My eraser button does not work. Awesome. Let's try this. Oh, that's so much better. Okay. Sorry about that. T. Okay, so at this point in the video, I've done 2 examples. Why don't you pause, guess what you think is going to happen next, and you'll see me write the answer. Hopefully you notice that P is times by both n and r, so I just need to divide out by those factors to cancel them. So I'll divide by n and r, and so n divided by n will be 1, r divided by r will be 1, and so to get t, I just end up with PV over nr. And that's it. That one's done. Woohoo! Got t by itself. And now to a new page. Alright, let's move on to another one of these. Hopefully you're feeling a little bit more comfortable as we go along. So for D, I'm going to be doing A equals BH over 2, which hopefully you recognize as the area of a triangle formula. You may be written it as like base times height times a half. And we, in particular, are going to be solving this for B. So hopefully you're anticipating what's going to happen. A equals B h over 2. So I've got 2 things sort of in the way of b by being by itself. It's being multiplied by h and divided by 2. So to get rid of a2, I'm going to have to multiply both sides by 2. So that'll cancel those factors. And to get rid of the h, I'm going to have to divide by the h to get rid of that factor. So b is going to be 2a over h. Isn't that fun? Good times. Ready for another one? Me in a room talking to myself by myself is super weird. Hopefully you recognize this equation if you didn't recognize any of the others. Oh my gosh, it's the equation of a line. Let's solve this puppy for x, because it's been a while since we solved for, well, anything. Just kidding, it was 5 seconds ago. Green today. Good times. So I want to get to x. X is being multiplied by m and then added to b. So the first thing that I got to get rid of is that plus b, because it was the thing that happened last. So I'm going to subtract b from both sides. So that'll add to make nothing on that side. And over here I'll get a y minus b equals m times x. And then since m is times x and I want to get x by itself, I got to do the opposite. So I'm going to divide by m to both sides. Since these are common factors, m divided by m will be 1. So I get that x is going to be y minus b over m. Hope you like that one. That one's a little bit more relatable. Remember, you can always pause and rewatch stuff and re-listen to the explanations. It's one thing that's nice about video. So we're moving on to the next thing. Applications. So the one thing that's nice about application problems when it comes to dealing with rational equations in general is that they always have the same steps for solving. So the first thing you want to do is you want to figure out what the thing is that you don't know. So you're going to let x be the thing that's unknown. Once you have that, what you want to do next is represent the other values in terms of x. So specifically be thinking make equations here. Oh my god, I hope you guys can't hear my cat meowing. She's at the door yelling. Oh, she can't help it. She's an old lady. Anyway, um, so as you're doing this representing of other values in terms of x, you're going to be writing these equations. You might have more than one, so you might have to combine some equations. So this is sort of a maybe unnecessary step. You won't always have to do this one. And I do this a little bit differently than what your book does if you read it. Okay, second to last step, solve. So you're going to be solving for the unknown. We're going to solve for x. Oops, I forgot the 4. I have to erase. All right, and then you should always check your solution because sometimes, it's good to know you're right. Big thing about this is since we're going to be dealing with real stuff more often than not, positive answers are going to be the only answers that make sense. So just be aware of that as we go forward. Okay, you're going to see the page jump in a second. So if you don't have all this down, you should pause at this point. Okay, so let's take a look at a fairly typical use of rationals, and those are work problems. So these are fairly they're also called efficiency problems. They're a very typical example of using algebra to solve some complex processes. So if Mary can clean her house in 4 hours and her daughter can clean it in 6 hours, how long will it take for them to clean the house together? So a common mistake that people will make with this is that they'll look at this and be like, okay, cool. So they're working together. I'll just average them. And they'll do 4 plus 6 divide by 2 and get 5, which is complete and utter nonsense because averaging 5 hours means that Mary should just work alone, that her daughter helping her clean the house did nothing for her, which just doesn't make any sense. So clearly averaging is not the way to go with this. So what you want to think about here is what you want to know, and that's going to be your x. So it's how long. This is all about time and rates and working. So time. Woohoo. So what you want to think about here is, well, they're going to fix and, do finishing one job. And I'm using the word job because I used cleaning the house here, but clearly it could be anything else like, cleaning up the yard or doing your work for the day or whatever your job happens to be, because I want this to be something you can apply to another situation. Anyway, so we're going to work together. So what you want to think about this is I've got time and I've got job, and then I want you to think about like work rate. So work rate will be like how much they complete per time. So your rate is going to be your job you get done over time. So if we wanted to look at how long it took somebody to complete a job, that should be, rate. That's supposed to be an R, and it totally looks like one, times time. Yeah? And that's how we're going to do this. So thinking about Mary and the house and everything, what we want to do is we want to complete one job, cleaning the house. And we want to look at Mary's work and her daughter's work working together. And I'm going to use plus because combined they should complete the whole job, one whole house. Yeah? Hopefully this makes sense to you. Okay, so, and that circle came out real good, right? Here's how we're going to do this. One job done. How long is Mary going to spend working on it? Well, the time she's going to spend working for that job is going to be X times her rate of completion. So in time X, she's going to complete a quarter of her work because it will take 4 hours. If X were 4 hours, she should be done, right? And then we're going to do the same thing for her daughter. Her daughter is able to do 1/6, so that if X were 6, she would be done. Get the idea? But together, they're going to contribute this much. Another way you can think about this problem, if you want, is you could say, hey, how much do they get done together in 1 hour? Well, in 1 hour, Mary should be 1/6 of the way done, and her daughter should be her daughter should be 1/6 of the way done, and Mary should be 1/4 of the way done. So together they would be whatever 1/6 plus 1/4 is. So that's how we're going to do this. So I'm going to rearrange this a little to make it easier to solve. So I'm going to think of this as x over 4 plus x over 6. And there we go. And these always look the same. Whatever the rate is times the time. If your time's the unknown, that's where you're going to put it, and so on and so forth. Okay, now watch this. So hopefully this looks like something you've seen before, and you remember your strategies for how to deal with fractions. So in looking at this, you should notice that, oh, well, I have two denominators. I should multiply by the least common denominator. And I don't want the keyboard, thank you. The least common denominator for these two would be, well, 4 is 2 times 2. That's totally a 2, right? Oh my god. I'm really annoyed the fact that the eraser on this doesn't work the way it does with all my other pen stuff. 2 times 2, and then 6 is 2 times 3. So I need at least 2 powers of 2 and a 3, so it's going to be 2 times 2 times 3, which would be 4 times 3, or 12. So I'm going to be multiplying this by 12 to get my denominators the same. So I'm going to take both sides and multiply by 12. I'm going to multiply by 12 and then times 12, because whatever I do to one side I have to do the other. So 1 times 12 on the left hand side is going to give me just a 12. Over here I'm going to have to distribute. So times 12 and times 12. X over 4, that's not a 4, times 12. I'm going to think of this as 12 over 1, plus x over 6 times 12. And I'm going to do some reduction to make this a little bit better. That's a why are my curves not coming out as good as they used to? I don't know. So 4 fits into 12 3 times, and 6 fits into 12 twice. So after you've done your reduction and the smoke clears, you'll get that 12 is 3x, because that's 3 times x, and 2x, because that's 2 times x. So you'll notice that I have 3 x's, then I have 2 more. I really have 5x. So to solve, I just have to divide by 5. So this is kind of unsettling because you should be like, oh, well, 12/5 doesn't feel like a nice number, does it? Nope. But you can reduce this. So we could rewrite this as 2 and 2/5 of an hour, which makes more sense because it's less time than Mary working by herself. So, and if you, that's totally what I wanted. It's awesome. I keep hitting things with my hand and then getting mad about it. Sorry about that. Anyway. So there we go. It appears that it takes 2 hours, and if you do 2/5 times 60, you can get the number of minutes that goes with this, which I think is 25 minutes. Let's check that to make sure your teacher's not crazy. I thought I had a calculator right here, but evidently I don't. Nope. I'm a liar. I have too many things open. Okay, so there's a work problem. Always ask yourself about how much work is done in 1 hour, because you're doing this in terms of time. Make yourself a lovely time to complete the job equation. That was this one. And then you're going to go ahead and solve for x, which will always be time with work. Let's go on to another example. So these are the ones that used to terrify people back in the day. Like, you ever done one of those examples where like a train heads east heading 20 miles per hour and then another train takes off from New York going 6 miles per hour, blah, 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 blah. How long does it take you to, read the dictionary? These problems are always crazy. So I've got you a rate problem. That's what we like to call these because it involves some kind of speed and people moving. So in this case, we're going to look at a boat. We know that in still water, which means having no current, so the boat's not being pushed in either direction by the current, it can go 20 miles per hour. It takes the same amount of time to get 3 miles down the stream as it does to go 2 miles upstream. Determine the speed of the current. So I'm going to set. Okay, so we got our river. This is, interesting. I'm going to note that my upstream is shorter than my downstream, so I'm going to make it look like that. So this is where we're going to start. So going upstream, two miles, and downstream, 3 miles. That's a 3. So as you think about this, you have like your boat. Drawing a boat from above. Let's make it like a canoe. I don't know a single canoe with people in it that can go 20 miles per hour, but you know what? Whatever. There's my people. Anyway, so one thing you have to keep track of here is that you appear to have some difficulty going upstream because you're fighting the current. Yeah? And our current is our unknown. It's the thing you have to find. You know that because it says to determine it. So my x is going to be the speed of the current. So now that I know that, I have completed step 1 really, which is determine the value of variable x. Now I want to represent my other values in terms of x. So I got to be a little bit careful here, and then I need to write some equations. So the other things I know is that I know some things about speed. The boat's normally going to go 20 miles per hour, but going upstream, the current's going to fight it. So really my speed going upstream is going to be 20 minus x. And then my speed going downstream is going to be faster because the current's going to help you. So 20 plus x. And I know that because I'm able to travel farther going downstream. The other thing I have hidden inside of here is that when you're traveling, hopefully you know that rate or speed is distance divided by time. Woohoo! Okay. The problem is I have a button on my pen that's supposed to be the eraser and it's not working. The button isn't, so it just ends up like me scribbling every time. So a couple things about this. I really don't want to have speed be the thing I'm equal to because my speed is different depending on which direction I'm going. So what I have to be careful about is I want to use something else in these information about what's happening in this problem to determine what I need to solve for. So this is relating to the stuff we were doing at the beginning of class where I was talking about solving for variables. So in particular, I know that it takes the same amount of time to do both of these activities, to go upstream versus downstream. Another way you can think about that is, oh, well, since I know about time, I should solve for time. So I'm going to multiply both sides by time to get it out of the denominator. It looks like the word time. So then I end up with time times speed equals distance, which hopefully makes sense to you because you're like, oh yeah, how far I travel is how fast I'm going, times how long I travel that speed. Alright, so then to get time by itself, I'm just going to divide both sides by speed. Which you maybe thought of this naturally, like, oh, I need time, so I'll just take my distance and divide by how fast I was going. Like, if I was, going to travel 400 miles going 60 miles per hour, I can figure out how long that would take me. That's what your GPS does when it tells you how fast you're going. So now I've established that time is going to be distance over speed. And hopefully you notice you have that information. Oh look, here's distance, here's speed. Here's distance, here's speed. And I know that upstream is equal to downstream in time. So that's what we're going to use. So here we go. I need to move my page up just a little bit so we can fit this. So what I've just established is that, hey, time up is time down. So I'm saying upstream is equal to time downstream. Okay, fixed it. Okay, time, that's supposed to be down. Okay, so going upstream, I'm going to do distance over speed. So going upstream, my distance traveled was 2 miles over 20 minus x. And then my time downstream is going to be doing distance over time, or sorry, distance over speed. So going downstream, I traveled 3 miles in 20 plus x speeds. I know this seems kind of weird, but there we go. Let's solve this. Hopefully, you recognize this as a situation from earlier last week, where we were like, hey, if I have two fractions that are equal to each other, God, I love it when this thing works. This one. Bring me to this page, please. Hopefully you recognize this as a situation where you know how to solve it. I got two fractions that are equal. That means I can cross multiply. So I'm going to multiply these two and set them equal to multiplying those two. So I'm going to have 2 times 20 plus x is equal to 3 times 20 minus x. So I'm going to distribute my 2, distribute my 3. So in this case, I'm going to get 40 plus 2x on the left side. That's a 0. Nope. And then equal to 60, because that's 3 times 20, minus 3x. Now I just need to combine like terms. So I like positivity, so I'm going to make my moves so that my stuff remains positive, and then I don't have to worry about negatives. So that means I'm going to add 3x to both sides to collect my x's to the other side. So over here I'll get 40 plus 5x is equal to 60, because 3x minus 3x will be just no x's. And then I'm going to subtract 40 from both sides. I'm going to run out of space here. Just a second to let me scroll up, because I have to use the little hand. Woohoo! So 40 minus 40, that'll give me a 0. Have that 5x left over. And then 20, because 60 minus 40 is 20. So then I have 5 times x equal to 20. Let's divide by that 5. So then I'll get that x is 4. So it appears that x is 4. And hopefully you remember from all the way back at the beginning that x is the speed of the current. So this has to be in miles per hour. And that's it. Okay, so just to review, when you're setting these up, be very careful. Think about what you know. Think about what's equal to establish that equation, because that's something that's always true about these rate type problems where you're dealing with speeds of stuff and comparing them. You're always going to ask yourself what's going to be equal. That was back here at the time up equals type down step, because that in particular is going to tell you, hey, where is my equation going to come from? So make sure you pay attention to that. Who's equal? Who's the same? And then you might have to, once you know who's equal, readjust your idea between speed, time, and distance to make sure you have the right one solved for. So there we go. That's it for today. I suggest you go do some practice on your practice problems. Those are the additional exercises. And once you've downloaded the file to start those, you'll notice that there's also the answers available for you to check yourself. I'm hoping to make some additional example videos of some of these problems. If you get stuck, come to my office hours. They're going to be online.